what I'm going to be talking about mainly is locating roots. And I'll mainly be talking about a couple of fields. So I'm going to be talking about, I guess, the complex numbers and the reals. I might say a little something about prime fields. I might say a little something about p-adics, but we'll see how far we get. So I wanted to start off from around 1620s perhaps. And there's work of Girard. And there's the fundamental theorem of algebra. And forgive me for going slow at the beginning, but I want to be kind to the audience for a little bit. So let's let f(x) be polynomial, written this way. Has complex coefficients, a variable with c not equal to 0. Then what we can say is that there are zeta 1 through zeta d complex numbers with this factorization. So in other words, complex polynomials, they split completely, and another way to say it is that they have must-be roots, but another way to say it is that a polynomial of degree d has d roots counting multiplicity. D complex roots counting multiplicity. What I mean by multiplicity is this factoring definition. So we say that a root has multiplicity m if that's the number of times that it shows up as a factor here. That's all. And it's a beautiful theorem. And I'm not going to say much about the proof, but I'll just say that, well, there's some interesting parts about the proof. I think around 1740s, maybe that was the first proof, attempt at a proof. That was, again, I'm sorry, D'Alembert. But no correct proofs, at least not by modern standards, until about 1920s or so. That was work with Ostrowski. And in fact, nowadays, well, there's many proofs. Gauss tried to prove it. Actually, all of Gauss's proofs have holes in them, unfortunately. There's a really nice article, actually, by my former advisor, Steve Smale, from 1980, where he points out all the flaws in all these different proofs of the fundamental theorem of algebra. So it is interesting that it took a couple hundred years to get the proof right. Many little analytic assumptions are kind of swept under the rug and are just sort of assumed and not really made clear. So maybe the quickest proof nowadays comes from complex analysis. And there's several other proofs. But what I wanted to get at immediately was something that I promised in the abstract. I promised that there's cute little pictures that you can draw to say something about the roots or maybe locate roots. And maybe the first picture we can draw is the following. And it's going to look really trivial. It'll get more interesting soon. So the definition I want to make for now is just that the Newton polytope of F, Newton polytope, oh, let's see. We'll call it this particular interval, we'll call this I, D, where I is just the minimum. Index overall Ck not equal to 0 of J. So in other words, this polynomial, the way I wrote him, the leading coefficient is non-zero, and these other coefficients could be 0. So let me just take a look at the smallest non-zero one. And that gives me my other endpoint. So I have this interval. So here's my Newton polygon. Goes from I to D. And the corollary of all this is that the number of complex roots, counting multiplicity, number of non-zero complex roots, counting multiplicity, is the length of the Newton polygon. Newton polygon is just an interval here. So there you go. All right, very trivial, but it's the beginning. I mean, I have a picture, I can associate a length with the picture, and I get a number out of it, and the number means something. Now, what I want to say is about the real roots. Real roots are a bit more subtle. You can say a lot about them. So there's a theorem of Descartes. Well, it's a statement by Descartes. It was eventually proved later on. This is from around 1637, and Descartes. And it goes this way. If f of x is now written slightly differently, I'm going to write it this way. C1 x to the a1. And let's see. Maybe I should be clear here. I'm saying plus epsilon. All these old results that I'm mentioning, they weren't stated in this form because a lot of things weren't available back then. So I just want to be clear that I'm adding a little bit to the statement. Likewise here, I'm adding a little something. They didn't state things this way. So ct x to the at with 0 less than or equal to a1. So it be less than at, like that. These guys are real. They don't have to be integers. And I also want the ci's not equal to 0. Well, the ci's are reals, non-zero. Then what I'm going to do is I'm going to partition the interval from a1 to at. So then partition this interval a1 to at into signed cells. Let's see. As follows. So you have your interval from a1 to at. You have a bunch of points in the middle. You have a2 and so forth. at minus 1. And I'm going to attach signs to them for the coefficients. So these will have whatever signs they have. I don't know. Could be this way, could be that way. It doesn't matter. Well, it does matter. I'll say the sign of this particular point of any AI, which is going to be defined to be the sign of Ci, and call a cell. So by a cell, I just mean a pair of consecutive points. K plus 1, alternating, if and only if these coefficients have opposite signs. So if they multiply, have to be less than 0. Okay, so I'm not done yet. So I define this polynomial. It's got t terms. You can say it's a univariate t-nomial. And the exponents are written in decreasing order. They have coefficients that are real. They have signs and non-zero. And here's the statement. The statement is that f has exactly the number of positive roots of f is exactly equal to the number of alternating cells minus a non-negative even number. So that's known as Descartes' rule of signs. And by the way, from this definition, it's not hard to see that this is actually less than or equal to t minus 1. So I define cells here. It could be all the signs alternate, plus minus, plus minus, plus minus, in which case every single cell is available, is alternating. Then if I have t points on this interval, there's going to be at most t minus 1 cells, and so that's as good as it gets. I could have no roots. I could have 1 root, 3 roots, 5 roots. Depends on the parity. Depends on how many alternating cells I have, but I'm down by an even number, or it could be 0. So that's Descartes' rule.
Who did you say gave the proof of this?
Oh, you got me. I don't remember who gave the first proof for Descartes' rule, because Descartes did not prove it. Now, I mean, I'll say something here. There's a nice proof by Josh and Wang. This isn't an American Mathematical Monthly article, pretty far out there, but it's been done for a long time. Now, Descartes dealt with polynomials. He didn't deal with real exponents, but real exponents are perfectly okay. Also, the number of positive roots, I keep on forgetting this, counting multiplicity. That's interesting. You can do that. So it's not just a distinct number of roots, it's actually counting multiplicity, which is pretty cool. So you look at these two results, the fundamental theorem of algebra and Descartes' rule of signs, and you think, okay, they're really cool, but they look very, very disparate. They look very, very different. And it turns out there's a way to put them together. So, and I should say, Josh and Wang's paper is very nice because it gives a very, very short proof. I mean, the entire paper is 2 pages long. The proof is actually not so bad. What's easy to prove is this. If you just want the upper bound of t minus 1, it's very easy to prove by induction, okay, and using Rolle's theorem. That's a nice exercise for calculus students. Proving this fancier version is a little bit harder, but if you wave your hands and you consider how things look like when they have even multiplicity or odd multiplicity, you can also get a pretty easy proof, okay, conceptually at least, if you turn yourself into a physicist or something. But now the question is, how do you put them together? Can we unify both results? And the answer is yes. And I'll just tell you the name of the theorem, and I'll give you a little illustration of it. So this is something known as the Wilder-Woodhead theorem. At least that's what I call it. And so Wilder published a paper in 1917 with something like this result, and Woodhead generalized this quite a bit and gave a lot of really nice results in this direction, and going very, very general. So I will state the theorem in a minute, but first I want to illustrate something. So let's see if this thing is hard. Oh, he's off, I think. Maybe let's turn them off.
Oh, the red light is off.
So let's see if it works. Maybe I just turn them off. He's off or on.
on.
Oh, now it's off. Okay, good. That's promising. Okay, so here's what I want to illustrate. So I have a picture, and I'm about to tell you what the picture is. So you're going to consider a family of trinomials, family of polynomials. And the polynomials are the following form. You take x to the 57 minus c, x to the 25 plus 1. Consider these things. And you're going to let c go from, or not just say c, like that, plus c, range from, let's see, -10 to 4 and back. Okay, so what you see actually, these are the roots I'm starting off at x to the 57 minus 10, x to the 25 plus 1. You see the roots are kind of clustered around this way. They seem to cluster around 2 circles. Forgive the blobs. So I was writing this code in MATLAB, and there's like different things I have to tweak. I forget how to make the roots look nicer and not be blobs, but that's what they are. So they seem to be clustered in 2 circles, and actually if you look more carefully, it's 25 circles on the inside and 25 blobs on the inside and 32 blobs on the outside. It's a total of 57. So it's 57 roots. And here's what happens: as you increase, suddenly the roots come together and it looks like a cluster in 1 circle. You should also observe there's a pair of roots here. Maybe I should go back a little bit. Let me go back. A little too fast. Going all the way to the beginning. There you go. There's 2 roots that are positive. They collide and then they become complex. And then I go back again, like that. So I go from a cluster, or 2 clusters of circles. The 2 circles come together instead of clustering around 1 circle. And then they go back again, 2 circles, and then back to 1 circle, and back to 2 circles. So it sort of keeps on going back and forth. So, I'll put this on again. the point is, if you look now, let's observe one thing. If you look at any angular sector, it looks like these roots are pretty, well, in terms of angle, they seem to be pretty evenly distributed. Now, they're kind of dancing around each other. But if you look at an angular sector of moderate size, the number of roots in an angular sector doesn't change that much. It changes by a little bit. So if you look all the way around, it's always 57 roots. But if you look, like say, on the right half, it's going to be about 23 and a half, 23, 24, 25 roots. If you look in a quarter, it's going to be, what is it, 6, 7 roots or something, 5, 6, 7 roots. So here's the theorem that I'm getting at. So Borhe's theorem has to do with number of roots in an angular sector. That's the way you unify everything. So let me shut this off. So Borhe says this. The Borhe theorem. Which really should be better known. Says the following. You let S be any angular sector of width theta in 0 to 2 pi. I'll say it's half open. I'll explain what that is in a minute. Emanating from the origin. Let's let n be the number of roots of f, a polynomial f, in S. Then something remarkable is true. The number of roots of my polynomial in an angular sector, by the way, the angular sector I said is half open. It looks like this. So you have a ray, you go off theta radians that way, counterclockwise. And I said it's half open. So you include everything. You include this bottom ray, but I'm leaving out that ray. So it's half open in that sense. So then n is exactly equal to the following. It's actually equal to theta over 2 pi times d plus epsilon, okay? So in other words, it's basically a fraction of d, fraction of the degree, plus an error. And the error satisfies an S property. It was really remarkable. Where the absolute value of this error satisfies two things. It's less than or equal to this weird-looking sum, 1 over pi sum from I equals 1 to t minus 1, absolute value of the argument of ci plus 1 divided by ci. Okay, and this is when your angle is strictly less than 2 pi. Or it's 0. This is when theta is equal to 2 pi. So you see, you include both terms, because when theta equals 2 pi, you're looking at the entire complex plane, and okay, I guess you should assume that all the coefficients are non-zero. If all the coefficients are non-zero, you have the 0 roots, so all the roots are in C star. They're non-zero complex numbers. The number of roots is D. You're eating up the entire angular sector, entire complex plane. To get Descartes' rule, so the fundamental limit of algebra is C equals 2 pi. And Descartes well, you take an angular sector of width, there you go, half open, like that, and you let the angular sector go down to width 0, and you include the positive break. And this word quantity here, well, that's actually the same thing as counting alternating cells, okay? Because alternating cells look for alternating sign, and when two things have opposite sign, it means it's negative or positive or negative, and that means that you have argument equal to pi, okay? So divide by pi, have pi's. So that's a really beautiful way to unify. And the key theme here is the following. There's just a really trivial observation with this. A key is that any non-zero complex number can be written this way. If you have any complex number, you can write it out as r e to the I theta. So this guy is greater than 0, and this guy is going to be inside of 0 to 2 pi. Polar coordinates. Okay, so we're Hessian is cool because it tells you what happens really naturally in terms of polar coordinates. Okay, now this is going to be generalized in a certain way. I'm going to look at a different field, and this notion of magnitude and phase is going to generalize or change in a way. So this is the magnitude, and this is the phase. But wait, there's more. So in the picture that I was showing you, maybe I'll call it up again. You don't have to change the camera, but I'll just put it up again for the audience. You see that the roots are sort of going between 2 clusters and 1 cluster. Okay, sort of it's the cluster on 2 circles or 1 circle. By the way, the roots are never exactly on the circle, they're just sort of clustered around. That's important. So here's what I'm going to say. There's more going on. In fact, the magnitude is highly structured. It's highly structured. While the phase, I don't know what else to say about it, but other than it's random, or maybe I shouldn't say random, maybe I should say equidistributed. It's kind of interesting. You have this dichotomy between structure and randomness. So part of the roots is kind of structured, and part of the roots is kind of random, or randomish, maybe pseudo-random or something. So here's what I want to clarify about the structure. So I claim that there's actually a way you can understand at least the norms of the roots. So I was talking about locating roots. I told you how to count roots, but here's a way to locate them. So in fact, we can roughly predict the magnitudes. And this is where another picture comes in. So our first trivial picture was in something coming from the Newton polygon and looking at length. There's something less trivial you can do. There's something called the Archimedean Newton polygon and the Archimedean tropical variety. So I will make the following definition. Arch-Newt, that's your Archimedean Newton polygon, is defined to be convex hull of the following set. I'll tell you what convex hull is in a minute. Of the set, what's going to be? It'll be A, I, minus log absolute value of Ci, as I ranges from 1 to t. Okay, so remember, the polynomial is written as a sum of Ci's x to the ai. So I'm taking exponent, comma, minus log absolute value of the coefficient. That's all I'm doing. So as an example, if I look at the Archimedean Newton polygon for 1 minus, 10, x to the 25th, plus x to the 57, that's going to be the convex hull. The convex hull is the smallest convex set containing. Smallest convex set containing. This guy, here, you have 1, that's the same thing as x to the 0. 1 times x to the 0. So it's 1 comma, 0 comma, minus log absolute value of 1. Okay, so it's 0, 0. this guy, well, he's over 25, whatever that is. Log 10, it's going to be 3 point something, something around that. So it's something around here. There's the point, 25 comma minus log 10. And then here's 57 at height 0 because the coefficient is 1. What's the smallest convex set containing these 3 points? It's going to be a triangle looking like this. All right, so far, so good, but what does this mean? Well, we need something else. We need something called the Archimedean tropical variety. The Archimedean tropical variety can be defined many ways. That's what's going to tell us what the absolute values are, what the norms are, what the magnitudes are. So the Archimedean tropical variety is defined to be this guy. The set of all w's in R, such that the maximum over all I of these absolute values, CIE to the AI times W, is attained at least two distinct indices. I and I prime. I'm going to call them J and J prime. Okay, so it's a weird looking definition. There's another alternative definition. Let's say it this way. So let me clarify here. This is the algebra you want to look at, and it has something to do with a polygon. Let me first give you an example. So this, what does this W mean? If you look at this polynomial, looking at our example, so for large absolute values of x, if you look at the monomials 1 minus 10x to the 25th and x to the 57, are these guys, which of these guys are going to dominate in terms of absolute value?
The last one?
Last one, yeah, or the last two, actually. So minus 10 and x to the 25 and x to the 57 dominate, rather than the absolute value. And in fact, there's a place where they match up. Okay? So the point is, for small x, something else is going to happen. 1 and minus 10x to the 25th dominate. So what I'm getting at is that if you write out the polynomial 1 minus 10x to the 25th plus x to the 57, if you want to be really sloppy, you can say, okay, for large x's, for large absolute values, I can throw away this guy and then approximate my value of my function with this. And for small values of the absolute value, I can I'll throw out the biggest term. These guys are going to be closer, and I'll approximate by this. And in fact, to be even more sinful, you could say for large values of the absolute value, I'm going to try to approximate my roots by solving this thing for zoo. And for small values, I'll try to approximate my root by solving this guy. And actually, it winds up being not such a bad approximation. It gives you exactly something close to that. And that's the logic. So there's another proposition. You might wonder, what is the connection with this polygon? More than one connection. So I'll say it this way. Archtrop of F is also equal to, is also the set of all W in R, such that W minus 1 is an outer normal to an edge of arch Newt. So there's kind of a convex geometric definition. So you have a normal vector pointing that way, normal vector pointing that way. And the normal vector has a form W comma negative 1. Okay? So that's exactly what the W is. So, okay. Another convenient definition. Why do I give you these different definitions? Well, this definition is a little bit more computable. So if you know anything about computational geometry, you can compute convex poles pretty quickly. You can figure out slopes and outer normals pretty easily, and you start computing things numerically. So By the way, this is also equal to the slope of a lower edge. So if you don't like thinking in terms of normals, w comma -1, you can also just say, oh, the slope of this guy is w. You can look at it that way. Okay, so I made all these definitions, but there's a reason I'm talking about this. Here's the result. So this theorem has precursors going far back, but I'll say that a modern version can be found in a paper from around 2013. I'll say it this way, that any root zeta, complex root non-zero of f satisfies log zeta, log absolute value of zeta, minus w less than or equal to log t minus 1 for some w in the Archimedean topical variety. In other words, the Archimedean topical variety approximates for you reasonably well the absolute values, log absolute values of your roots. So this gives you some way to predict where the absolute values are. And so this is what's happening. The reason you see that picture over there is because for a trinomial, there's going to be two lower edges, which means the Archimedean topical variety is going to have 2 points. And the theorem is saying that whatever root you look at, log absolute value of a root, is going to be close to one of these guys, either close to here or close to there. That's what happens. Okay. So that's something you can do with the complex numbers. And the cool thing is that you can actually continue doing this over other fields. So let me see how I'm doing that time. So it's 34. All right. So before I go on, are there any questions? Yes?
This, to me, it seems like the set of W is finite.
Yes, it is. It's
okay.
finite.
In what sense is it a variety? It's like finite with points.
Right, it's going to be finite.
Okay.
but the thing is, all this generalizes. This generalizes the higher dimensions even. And when you go to higher dimensions, you get nice stuff. So I'm glad you asked about that. So yeah, that's certainly true. I mean, varieties, zero-dimensional varieties are typically finite. So thing to observe is that all this extends to n variables. So as an example, I'll just draw one little example. Everything extends. So the reason I give you multiple definitions is that these multiple definitions, they extend in different ways. If you were in the 17th century, or 18th century, in the time of Newton, you would have actually thought of it in these terms. Actually, the reason Newton polygons are called Newton polygons is because they go back to Newton. So he was looking at a different field, and he was looking at Puiseux series expansions of curves and things like that. He looked at slopes of a certain polygon, something like that. But this doesn't generalize the higher dimensions. This generalizes the higher dimensions, because you can talk about a lower facet of a polytope, and inner normals and outer normals. This also generalizes. You can talk about monomials and where they're maximized, different regions. So all this generalizes the higher dimensions. So as an example, if you let f of xy equal 1 plus x plus y, then actually you get the following picture. The Archimedean topical variety looks like this. It's a piecewise linear object. The origin is here. The slope is 1, 1. That's horizontal, left vertical. And then log absolute value winds up being something which looks like an amoeba, in the sense that it has tentacles in the body. So you get this. So the log absolute value of the complex zero set of f is in red, and it looks like an amoeba. And the Archimedean topical variety is in blue. And what I said remains true. Any point, any complex zero of f is going to lie within distance log t minus 1 of some point of the tropical variety. So this tropical variety, this piecewise linear thing, approximates the pink thing. So that extends. But okay, what I want to get at, I want to say a little something about phase. And phase is where things get really, really weird. So just to recap. The fundamental theorem of algebra says something about the number of complex roots. Descartes' rule says something about the number of real roots. And then we have Wilder, says something about how the real roots sit inside of the complex roots. I mean, it gives you a lot more refined information. And this other theorem, AKNR, says something about magnitudes. I should also say more. This theorem has precursors. So the version we proved something in arbitrarily many variables, and we were very happy about the result. But in one variable, there is work of Hadamard and Ostrovsky. So this goes way back. Hadamard observed something a little bit like this, not exactly like this. And Ostrovsky observed something a bit like this, but he didn't think in terms of sparsity. He thought in terms of polynomials of degree D. So his results are stated a bit differently. But this is from around 1940. This is from around 1880s perhaps? I forget exactly. So a lot of this work on polygons or sort of the convex geometric aspects of zero sets goes way back. And there's lots of really beautiful literature that not enough people know about. So I just want to highlight that. So okay, we've spoken about locating roots in different ways. And now I'm going to switch gears a bit. Because for the rest of the talk, I'm going to be a little bit more number theoretic. And maybe I'll end or say something about a really strange phenomenon having to do with phases. So what can I say about phases? So one metaphor that I want to get across is the following. So this notion of magnitude and phase, angle and so forth, this is definable over the complex numbers. If you're to think about a different field like the p-adic complex numbers, hard to draw a picture, but I'll try to draw a picture. So what you have going on over the p-adic numbers is expansions base p, they go on forever. And what's most important for determining the norm, or one of the things that determines a p-adic number, is the notion of most significant digit. Okay. So what I'm getting at here is that the notion of phase over the complex numbers somehow corresponds in some weird way to the notion of most significant digit. So I at least wanted to say that before getting too technical. And what I'm going to try to do, I have to define what most significant digit is, I might have to define what valuations are, I might have to define many other things, but I want to try to keep things as simple as possible. Let's just talk about finite fields for a bit. Okay. And I want to highlight an open problem, which is really irritating and more people should know about. Because I want to know more people. So let's think about FP for a minute. So this is the finite field with P prime number, many elements. Of course, we might know this as C mod P, if the integers 1 over P, the arithmetic is pretty reasonable. And here's the problem I want to think about for a minute. First of all, why am I mentioning a finite field? Phase is first digits. When you forget about norms, when you forget about sizes and metrics and things like that, and all you care about is the phase, or digits, then you're kind of in the land of finite fields. Okay. Non-zero digits, they're 1 through p minus 1. whether you're a finite field or whether you're a QP or CP. Okay. So let's think about how many roots a polynomial might have over a finite field. Let's think about sparse polynomials. This Descartes rule gave you this really nice bound. It told you the number of roots is the most t minus 1, number of monomial terms minus 1, independent of the degree. And the question is, does this persist over finite fields? So is there a finite field Descartes rule? That's a really good question. Or bound. So let me say yes and no. Tell you why. So the answer would be no for a reason, but the answer will be yes for a reason. So if you know anything about number theory or just a little bit of basic algebra, you could look at this way. You could look at x to the p minus 1 minus 1. Okay, that's two terms. Has p minus 1 roots in the finite field of p elements. You might know this from a basic algebra class. Okay, so Fermat's little theorem. Okay, so you think, okay, you're dead because here's a polynomial with two terms, and the number of roots is way more than 2. In fact, it's degree many, so that's pretty bad. But I would say the answer is yes still, because, however, there is just one coset. And that is the key. So it turns out that if you look at sparse polynomials, the number of cosets is small. It's boundable in terms of the number of terms. So maybe we can still recover some kind of result. And so it turns out that you can make this more quantitative. So if you go back to work of around 2000, and you have Nettie, Friedlander, Konyagan, Lehman, and Schwardinsky, I think, no, Schwardinsky. Oh, Larson, also Larson. I think perhaps Schwardinsky was there too. Memory eludes me. They proved that for any univariate polynomial, polynomial one variable, t terms, there are on the order of this many cosets. So I believe it's t minus 1 over t minus 2 over t minus 1. Cosets with the roots. Okay, that's a fancy way to state it. But there have been improvements. And so one of my students actually did a very nice refinement of this. So this is Xander Kelly, 2016. He got this down to about 2 times p t minus 2 over t minus 1. That. But I want to be more specific. This is sort of a little bit abstract. I want to be more concrete. So let me just consider this more concretely. Here's a theorem. So this follows work of Jingguo Bi and Cheng and myself and Dajun Wan. This was around 2017. And also Senator Kelly. Actually, this is around 2015. And Kelly, 2016. 1 minus 1. Any trinomial over P has at most 4 1/2 plus square root of P minus 1 roots in FP. Sorry, we polynomial this form. I want to say this guy, this x plus c3 x dn. There, this guy has the most many roots in FP. And the CIs are non-zero. Okay. So again, very, very weird looking. I mean, I was talking about cosets. Why did I talk about cosets? The picture that I showed you actually was cosets, believe it or not. So over the complex numbers, those clusters of roots, those are actually approximate cosets. Those are arranged close to a circle. A circle actually is a kind of a coset. So this phenomenon of cosets persists over many different fields. Okay. That's something I want to get across. But more concretely, this is a provable bound, and the conjecture is that the bound should actually be something like this. It should be 4 log p over log log p. And this is open to this day. It's been verified up to some rather large primes. So this is known for p up to about 72,000. So the experiments are a little bit less trivial than you think. I mean, you would think nowadays you can get everything up to 1 million, but actually we searched over all possible triples and all possible degrees. And so this takes a while. So I had some students look at this. And the reason this is interesting is because there's kind of a bit of randomness here, because it seems that the roots of these guys tend to behave very, very randomly. And so I spoke to a friend, Karen Kedlai, and so Karen Kedlai suggested that there might be some kind of a heuristic for this. And he sort of suggested this heuristic of balls and bins, and there's a way to model it probabilistically. And that way he came up with an estimate around this. And we checked this, and actually it works out pretty well so far. Okay, that's what I want to say about quantum fields. And before I say some final results, I just want to check if there are any questions. So we're talking about locating roots over various fields. There's notion of magnitude and phase. I just revealed that actually the commonality for everything is actually cosets in some sense, at least in one variable. I mentioned some kind of word angular metaphor. Now I'm going to go more into this angular metaphor. So the question is now, what about P? So, long story short, the p-adic integers one way to think about them is just infinite expansions of the following form. Say, let's see, p0 plus a1, p plus a p squared, like this, where the ai's live inside of 0 to p minus 1. And a certain kind of arithmetic on them. So the way you define the arithmetic, to say it really, really roughly, is that you allow carries infinite. That's a really fast way to put it. So as a simple example, -1 is equal to 2 plus 2 times 3 plus 2 times 3 squared, infinitely so far, in Q3, sorry, in Z3. Why does this make any sense? If you add 1 to both sides, 2 plus 1 is 3. The 3 comes over to here, and then you get this infinite cancellation, and you get 0. So that's why -1 is equal to this over the 3 adic integers. Okay. So what's important for us is that the p-adics are a different completion of Q. Q with respect to a different method. So in some weird sense, they're a cousin of the reals. And everything we've done over the reals and complexes can be done for the p-adics and beyond. So the metric you can define this way. So let's let board p of x for any x and z. This is equal to, let's see, written this way, p to the k times q with p naught dividing q. So if I factor an integer x into a power of p times q, then I have this, like that. So it's just the power of p that I have in the factorization for this integer. And this valuation can be extended to rationals. And go this way, so just take order p, x over y, that's just order p of x minus order p of y. And of course, order of 0, that's defined to be plus infinity. And now I get a really strange definition. You let p-adic metric, rational number x, be defined as p to the minus order p of x. So this is how we're going to define a metric on Q. And this actually is a metric. You can check all the properties, but it satisfies a stronger version of the triangle inequality. And you can complete it in the sense of analysis, and you get this field minus QP. All right. And why is this interesting? Well, there's numerous applications of the p-adics in number theory, but the thing that I want to get at is the following. Over the complex numbers, we could predict the absolute value of a root of a polynomial equation up to some error. What's really cool is that over the p-adics, there is no error. You actually get the norms exactly. So over CP, that's p-adic complex numbers, and that's defined to be the completion with respect to the p-adic metric of the algebraic closure of QP. You can predict norms exactly. And the way I like to say it is that the complex numbers are kind of mushy with respect to the metric, at least in terms of when it comes to polynomial equations, whereas the p-adic complex numbers are crisp. The norms are somehow a little bit more on the nose. So the theorem that I gave you about predicting norms of roots has an older analog over the p-adics. It's about maybe 100 years old. Maybe. What time is this? I'm almost done. So recall, there's a Newton cancel theorem. So what you do is you let the p-adic Newton polygon of F be this thing. Let it be the convex hull of the set of points of the following form: AI, ord, P of Ci, I going from 1 to T. So remember, I had a polynomial, T terms, one variable. And before, for the Archimedean Newton polygon, I had exponent, comma, minus log absolute value of the coefficient. Now I have the p-adic valuation of the coefficient instead. And here's what happens. Then, well, also can let p-adic tropical variety, of P, be defined to be the following. Multiple definitions. So one definition is a set of all W in R such that, now if the normals point the opposite way, omega comma 1 is a inner normal to an edge WP. And happens. Then if you look at the ORD P of the p-adic complex zeros of the polynomial, it's exactly equal to the p-adic comparable variety. So this is actually an old theorem. And what's remarkable is, like I said before, all this extends to higher dimensions. These extensions to higher dimensions are due to various people. But I'll just say briefly the following. This all extends. So this work from around 2000 of Kapanov that extends this very, very naturally. So a p-adic polytope in higher dimensions, you can define the p-adic tropical variety, and now the theory is really beautiful. If you look at the p-adic evaluations, you get them exactly. So the final note that I want to end on is the following. So final note. There is a higher dimensional version of Descartes. And that is known as Khovansky's theorem on real polynomials. So that theorem tells you that if you have n equations, n unknowns, and you have a bound of the number of terms, then you can get a bound for the number of real roots, isolated real roots, solely as the number of variables and number of terms. Really beautiful result. And getting the tightest possible bounds is still an open question. It turns out you can extend this to the p-adics as well. This also extends to the p-adics. To QP. So that's work of Denif and Vandenbries. From 1988. And work of other people as well, Leinster, in 1997 or so. So I've done some work in this direction as well. So something I want to end on is just an open problem. It's an open problem to get really nice explicit bounds for the number of roots of sparse polynomial systems over the p-adic rationals. So there's a whole host of difficult questions there, which I'm not going to get into right now. But I just wanted to give you a survey of some of the ideas behind phenomenal theory over different fields. And it's really a beautiful theory. And it even has applications. I can say more about that later. But I just wanted to end now. I've already been talking for long enough. So thank you very much.